Hi everyone. I'm going to talk about a problem in number theory related to Artin's primitive root conjecture that I submitted for the benchmark. To state the problem, I need to introduce a little bit of notation. So, first we let Vp of n denote the exponent of p in the prime factorization of n. And second, we let odd p of a denote the multiplicative order of a modulo p. And finally, a non-standard definition, we let the truncated order of a modulo p be equal to the order of a modulo p, except that in the prime factorization we omit all prime factors that are larger than x. Now, the problem can be stated as follows. We look at the primes p for which the truncated order of 2 is greater than the truncated order of 3. And we let dx denote the density of such primes p. We then want to compute the limit of dx as x goes to infinity to 7 decimal places. Now, first of all, the truncation is a technicality, and what we're essentially asking for is the density of primes p such that the order of 2 modulo p is greater than the order of 3 modulo p. And this problem is very much related to the famous Artin's primitive root conjecture, which asks whether there are infinitely many primes p such that 2 is a primitive root modulo p. And this conjecture has been solved under a generalization of the Riemann hypothesis by Christopher Whewley, but is unconditionally still open. And for technical reasons related to this, we truncate at x in the problem statement so that one can solve the problem unconditionally. And lots of variations of the conjecture have been studied. Let me name a few. So first, one can look at simultaneous primitive roots. Second, one can look at near primitive roots. And third, one can look at a so-called two-variable Artin conjecture. And finally, one can also look at the equality of orders and the ordering of the multiplicative orders modulo p. And in all these cases, the infinitude of such primes p has been solved under the generalized Riemann hypothesis, but actually computing the density of the relevant primes p is more complicated. In particular, unlike in the four of the first cases, where one can give a closed formula for the density, in the last case, no clean formula exists. And I came up with this problem because in one of my papers I actually posed the problem of computing the density such that the order of a modulo p is greater than the order of b modulo p. And as mentioned, this turns out to be more difficult because there actually is no formula that is as nice as in the other cases. So in order to solve the problem, one first of all needs to be familiar with the methods used to solve this kind of Artin type problems, and second, one needs to overcome the difficulties that arise due to the lack of nice formulas for the density. And with this motivation, let's move forward to the actual solution. I've decomposed the solution to 4 parts. The first part is that we actually have explicit formulas for the density of primes, such that the truncated order of 2 is equal to p minus 1 over a, and the truncated order of 3 is p minus 1 over b. The actual formulas turn out to be quite complicated, but for all purposes, the relevant facts are that 1, we can actually compute these densities, and second, the formulas involve a product of a primes q not exceeding x. And the proof idea is that this condition on 2 is equivalent to a certain type of power residue condition on 2 modulo p. Namely, that 2 should be an 8 power modulo p, but no more. And these conditions can then be handled by a Galois theory, and in particular the Chebotarev density theorem. And together with an inclusion-exclusion argument, we get the densities dA/B. In the course of the proof, one needs to be able to calculate the degrees of these field extensions where one adjoins a root of unity, a root of 2, and a root of 3 to the field of rational numbers. These degrees turn out to be mostly what you would expect, namely phi of n times a times b, except that the square roots of 2 and 3 lie in cyclotomic fields, so one needs to, in some cases, adjust this naive guess by a factor of 2 or a factor of 4. But aside from that, we now have an explicit formula for these densities, and one may now ask, why couldn't we just calculate the density in the problem statement by computing these densities dA, B, x for a and b not exceeding 1000 and x being equal to 1 million, say. And the answer is that while this gives a decent approximation, it's not accurate enough. So one gets maybe 3 correct digits, but we actually need 7. So the naive approach is simply too inefficient. And therefore we need to first of all come up with a more efficient way to compute these sums. And then we need to bound the errors from only summing over a subset of all a and b, and from using a finite value of x. So let's then consider how to do this summation more efficiently. So our previous approach can be visualized as follows. What we want to do is to compute this sum here in gray, and we approximate this sum by computing this sum here in red. And the issue here is that this leaves a lot of the mass of the sum here to the remaining part, so the approximation is not very tight. And the solution is that we instead compute the sum over this whole region here, pictured in red in grid A, and we do this by first computing the sum over all of these columns, and then subtracting a finite triangle from the sum. And the reason why this works is that it's possible to very efficiently compute the sum over a whole column here in picture B. Essentially because when we're summing over all values for the multiplicative order of 3 modulo p, this means that we're basically disregarding the order of 3 modulo p altogether. So we're in the same situation as in step 1, except that we only now have to care about the order of 2 modulo p, not about both the order of 2 and order of 3 modulo p. And the sum in grid C, namely the sum over the triangle, is computed in the obvious way, so you simply go through the cells one by one and compute the values. And the benefit from all this is that we got the rectangular region in picture A for free compared to the previous approach, which then gives you a much better approximation of the whole sum. And what remains is to make these claims about these approximations being good quantitative. So first, how much do we lose from omitting some of the terms in the sum, namely the green region in the picture? To do so, we bound the density at A and B, the formula being that this density is at most a constant times 1 over the phi of the least common multiple of A and B times A times B. This bond turns out to be essentially tight up to a constant factor, unless the density is 0, of course. And for the phi function we have the well-known lower bound of the form n to the 1 minus epsilon that we can use to further upper bound the density at A and B. And routine work then gives you a tire bound that's roughly quadratic. So the error terms is roughly 1 over t squared when t goes to infinity. But in practice we need to have bounds that work for finite values of t instead of simply asymptotics. So you need to work this proof through with explicit constants. But this is not a major issue. And finally, we need to bound the error coming from taking the limit at x goes to infinity. So we need to account for the effects of truncating. And what this boils down to is bounding a product of a primes q larger than x, namely of 1 minus 2 over q squared. And again, routine work gives you a bound here of the form 1 over x times log of x. And once again, we need to work with explicit constants to get a bound that works at a finite value of x. And that's it. So what remains is to actually do the implementation. So we implement the computation of the density at A and B and the density at A. And then we take the value of the parameter t at 2 times 10 to the 4th and the value of x at 2 to the 8th, which then gives you a small enough error bound that you can prove that the first 7 digits go correctly. All this is pretty fast, only 20 seconds in C++, and the answer turns out to be that the density is roughly 37%. Hope you enjoyed the problem, and bye!